Hey there. Well, I hope you're all doing well. Um, Thanks for joining me today. We're going to be talking about assignment 69. 69 is all about solving log and exponential equations. Okay? Um, just before we get to that, um, could you please condense or simplify each expression? The first one is log base 3 of x plus log base 3 of 5 minus log base 3 of y. Okay, I remember when I have two logs joined with addition that I could combine those into one log where things are joined with multiplication. I remember when I had two logs joined with subtraction, I could combine those into one log involving division. Yeah, and I'd probably put that base 3, 5x over y. Nice. Okay. What if I had something like this? 2 Can you condense that for me? Good. Power rule has to come first. And so that's going to be log base 5 of x squared minus log base 5 of z to the third plus log base 5 of y to the fourth. Once I've pushed all those powers back up, now I can use my log property to combine these. Remember, every time I see a minus, that goes on the bottom. And every time I see a plus, that's going on the top. So I'm going to have log base 5 and x squared on top, because this is positive x squared. Ooh, a y to the fourth on the top, because this is also positive. And because of this minus, z to the third on the bottom. Okay? All right, so let's get to looking at solving. So the first bunch I want to look at are exponential equations, like 4 to the x equals 16. You know, we did some problems like this in our Algebra Basics unit. And we said, you know, if we wrote these so that they had the same base, because the bases are the same and the terms are equal, we know the exponents must also be equal. Okay? That's probably the easiest way to do that problem. We could look at this problem in a number of different ways. We could graph this in y1. It's an exponential growth curve. We could graph this in y2. And we could ask the question, where does this exponential growth curve intersect the line y equals 16? Yeah. So, so that's one way. There is another way where we're trying to get at this. And I think about using the power property that we were just playing with in the last video, well, even in our bell work. The power property allows me to bring that x down. And since I want to solve this equation for x, I really want to get it down. But that power property only works in the presence of a log. So I could take the log of both sides. That would then allow me to bring this down. X log 4 equals log 16. And that x is attached to the log 4 with multiplication. So to get x by itself, I've got to do this. Now, I will say that many students want to cancel that and want to cancel here and want to arrive at the number 4 as their answer. Well, so here's why that's not a good idea. These things are supposed to be equal, right? And we already know because we just did this problem, that the answer is 2, not 4. If I plug that 4 in here, I get 4 to the 4th, which is 256. That's not the same as 16. So this, you can't do that. That's you imagining a math. It's not real math, so stop doing that. Instead, I could, in fact, though, do some stuff with this. I could say, okay, so up top, I've got log of 4 squared over log of 4. And then I could use my power rule to bring down that 2. 2 log 4 over log 4. Those cancel, and I'm left with 2. So there's a second way of doing the problem. In fact, when I look at this, 4 to the x equals 16, I don't have to take the common log. I could do the ln. And then divide both sides by ln of 4. Notice this is 2 different logs. This is not the same as log 4 minus log x, which can be written as 1 log with 4 over x. This is not this. This is me using my log property to condense these 2 terms to 1. This is me taking 1 log and dividing it by another log, because I'm following PEMDAS to get x by itself. Now I could say here that 16 is 4 to the 2nd, and bring this down to ln of 4 over ln of 4, leaves me again with 2. Okay? So there are ways to do this wrong, but there are a bunch of ways to do this problem correctly. Okay? I think the easiest one is where we rewrite the base. And I would recommend that on all the exponential problems we're going to look at today, I believe. So let's take a look at this. 3 to the x equals 243. Okay, so we want to rewrite each side so they have the same base. This base is 3, so I want to remember that this is 3 raised to some power. What power? 5. 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 4, and 3 to the 5. Okay, so that's 3 to the 5th. Since the bases are the same and the terms are equal, the exponents must be equal as well. Okay, x equals 5. But we could, of course, look at this problem a different way. We could take the ln of both sides. And the only reason I'm taking the ln of both sides, is so that I can, maybe I'll come back and do it again with log base 3. The only reason I'm taking the ln instead of log is that it's one symbol less to write, and no, really, I'm that lazy. So x ln of 3 equals 5 ln of 3 when I use that power rule. And if I divide both sides by ln of 3, I get x equals 5 again. Okay? But what about taking the log base 3 of both sides? Well, it has its merits. So if I do the log base 3 and the log base 3 of both sides, I can bring the powers down. And now I have x log base 3 of 3 equals 5 log base 3 of 3. Well, what is log base b of b? We know that that's 1. Of course, you could divide both sides by the log base 3 of 3, and those would cancel out, also leaving you with x equals 5. Great. So, how about this one? 7 to the x equals 1 over 49. Why don't you pause the video and give that one a try. Okay, so remember, we want them to have the same base. So that has to be 7 to the negative 2. Why? Because this is 1 over 7 squared. But this is up top. This is on the bottom, so I need to move it up top. So 7 to the minus 2. And if 7 to the x equals 7 to the minus 2, since the bases are same, terms are equal, I know that x equals negative 2. Okay? How about 9 to the x minus 1 equals 27? We solve that equation. I mean, I'm still thinking about this graphically. Horizontal line, exponential growth curve, shifted right 1, they intersect somewhere. Only once. I'm only expecting one solution here. Okay, so I need to rewrite them so they have the same base. I guess you could say this is 9 to the 3/2, but very few students think that way. Instead, I'm going to rewrite them so that they both have a base of 3. When I raise a power to a power, I multiply those powers. And since the bases are the same and the terms are equal, these exponents must be equal. 2x minus 1 equals 3. 2x minus 2 equals 3. 2x equals 5, because I added 2 to both sides. And so we know that x equals 5/2. Fabulous. So at x equals 2.5, this exponential growth curve will intersect this horizontal line. Okay? I think that last one is reasonably test or quiz worthy. How about this one? 32 equals 4 to the 3x plus 1. Will you solve that exponential equation? Hey, welcome back. Did you rewrite them so they have the same base? Well, that same base isn't going to be 4. It's going to be 2. Don't forget, when you raise a power to a power, that you need to multiply those. Since we have the same base and the terms are equal, the exponents must also be equal. This 2 has to get applied to that, not just that. This is distributing. 5 equals 6x plus 2. 3 equals 6x. X equals 1/2. Okie doke. Okay, how about some loggy things? ln of x minus ln of 2 equals 0. What can we do here? Well, I can think of a couple of things we can do here. The first, since we just talked about log properties, would be to say, oh look, 2 logs joined with a minus. That means I can write this as 1 log where there's division. But now what? Well, I have to get rid of this. What undoes log base e? Well, the inverse would be e to the. So, remember, e to the, log base e, those cancel because they're inverses. And so we have x over 2. E to the 0, 1. And if I multiply both sides by 2, I get x equals 2. Remember, since logs have restricted domains, i.e. I can't take the log of 0, or can't take the log of a negative, I want to make sure that when I plug this back in, I'm not asking ln to take the ln of a negative number or of 0. But when I do plug that 2 in, I get ln of 2 minus ln of 2, and that's supposed to be 0. Sure, that's 0. Yeah, I like it. So there's one approach where we condense first. Most students don't want to use the log properties. Instead, they want to do this. And so now they've got ln of x equals ln of 2. We still want to get rid of, we still want x by itself, so we still have to get rid of this, which we can do by exponentiating. That's how most students do it, and generally that's fine. There are some problems, though, where you actually need to be doing the condensing, and that's going to happen when we have more than one log on a side. Okay, how about this one? ln of x plus ln of 5 equals 0. I like to think you can do this from your comfortable place. Of course, if you don't remember your log properties, this will be a lot harder, because I'm going to condense here into ln of 5x equals 0. I'm going to get rid of the ln by exponentiating. And so I have 5x equals e to the 0 is 1. And so x equals 1/5. Now, for those of you who didn't want to combine these into one log, and instead thought, I'm going to subtract ln of 5 from both sides. Minus ln of 5 minus ln of 5. So now it looks like this. I can't exponentiate yet. I have to deal with this -1. It's a power. I got to use the power property in reverse. ln 5 to the -1, which is the same as ln equals ln 1/5. Nice. And now I can exponentiate, and I get x equals 1/5. Ta-da! Same, same. A lot of people mishandle this, which is why I like one of the reasons I like condensing more. Okay, so let's now take a look at solving these exponential equations. Yes, I am going back. I like going back and forth with this because it forces you to think a little bit more. On our test for this unit, I'm not going to specify a method. I'm just going to say solve these. So how do we solve this? Well, when we did our first exponentials today, we said, well, the most common way is to rewrite the base. Yeah, I don't know how to rewrite this as e raised to some power. So not going to do that here. Instead, I'm going to focus on this. This thing is up here in the exponent, and I want it down. I want it down on the same level as this e and this 4. So my recommendation is that we take the ln of both sides, because then I have a log and I can bring down that x. We talked about the ln of e a few videos ago, also known as log base e of e. What's the ln of e, or the log base e of e, equal to? That's right, 1. And so my answer here is x equals ln of 4. Done, done. Can you solve this one for me? Welcome back. So this is different, isn't it? And you know, I can see a lot of you doing some really focused work, a lot of algebra. I want to think about this graphically for a moment. Over here, I have an exponential growth curve, and here I have a horizontal line. And this problem is asking, when does that exponential growth curve intersect that horizontal line? Well, here's the exponential growth curve that passes through -1, 1 over e, 0, 1, and 1, e. And we're asking the question, when does this curve intersect that line? And the answer is never, because there's this horizontal asymptote at y equals 0 on e to the x. This curve approaches 0 but never gets to 0, and so certainly can't get down here to -3. So this has no solution. Now, I understood that and saw that graphically So I didn't go any further. But if I were to take the ln of both sides, over here I could certainly bring down the power rule. And then the ln of e, well, that's log base e of e. We know that's 1. Now, what about this? Well, yeah, that's the issue, isn't it? Because remember, I can't take the ln of a negative number. And so as soon as I take the ln and see it's the ln of a negative number, I should say no solution. These things do not intersect, okay? All right, so then, will you be so kind as to solve this equation? I mean, again, it's the e to the x exponential growth curve shifted left 2, and I'm wondering when that equals the horizontal line y equals 7, okay? Okay, so yeah, I can't rewrite them so they have the same base, but I can take the log of both sides and bring this down. So we've got x plus 2 ln of e equals ln of 7. Now, ln of e is, yes, 1. So I've got x plus 2 equals ln of 7. And I want to get x alone, so I want to subtract 2 from both sides. X equals ln of 7 minus 2. Though I kind of want to write minus 2 plus ln of 7, so you don't inadvertently think that this is supposed to be inside of there. All right, now remember our original equation was exponential, e to the. There's no restriction on the domain of an exponential function. So this is an ought check at best. This is not at all a must check. If I started off with logs or ln's here, that's when I have to go back and check my answer to make sure I didn't get, I'm not in the position of taking the log of a negative or the log of 0. Okay, next. Well, how about this one? This seems a little more exciting. 5 times 10 to the x minus 1 equals 1. Yeah, what do you do here? Well, you know, divide by 5 seems reasonable. And I've got 10x to the minus 1 equals 1/5. And I can take the ln of both sides. I could also take the log of both sides. Remember, log, the common log, is log base 10. So log base 10 of 10 to the power of, those are inverses and cancel each other out. And now if I just add 1 to both sides, I'm going to be good to go. X equals 1 plus log, not enough space there. X equals log of 1/5 minus 1. Oh, plus 1. We added 1. That's fine. I like that. But here, you might think, well, isn't that the log of 1 minus the log of 5? And what's log of 1? Yeah, that's 0. So x equals negative log 5 plus 1. Or I guess 1 minus log 5. Okay, so we can do this problem that way. That's one way. Do I have another way? Well, what if instead of taking the log of both sides, so that I could cancel the log and the 10 to the power of, what if instead I had started this problem with 10x minus 1 equals 1/5, and I took the ln of both sides? I still have to bring down this power. and that's great. But I'm solving for x. So I need to divide both sides by ln of 10. No, you cannot cancel those. No, you cannot cancel those. Stop it. But I still need to add 1 to both sides. So 1 plus ln of 1/5 over ln of 10. By the way, this is the change of base formula we've talked about a couple videos ago. Do you remember what this is equal to? This is equal to log base 10 of 1/5. If I use the change of base formula on this, I get that part. Okay? Okay. So let's go back and do some exponentials. I mean some logs. ln of x equals -1. Okay, I want to know when this curve hits that horizontal line. I should already know, because this point is E1, this is 1, 0, and this is 1 over E -1. When does this curve intersect the line y equals -1? Oh, here, x equals 1 over E. And you know, I could check that by saying, well, what is the ln of 1 over E? Well, that's the same as the ln of E to the -1. And then, because I have a log here, I can bring that -1 down. And what's the ln of E? Yep, the ln of E is 1. 1 times -1 is, in fact, -1. So that's one way for me to think about this. You don't have to think about this graphically. Certainly helps. You could also exponentiate. These will cancel, and you'll have x equals e to the -1, or 1 over e. Ta-da! All right, so hopefully you'll be comfortable with this one. ln of x equals 8. Can you please solve that log equation? Did you exponentiate on both sides? I hope so, because then you could be done in one step. X equals e to the 8th power. Nice. What if instead of an ln, we have log base 4 of x equals 3? How do I get rid of this? I know I get rid of a log by exponentiating. What am I going to exponentiate both sides with? That base, 4. I need to use 4 as a base on both sides. I need to exponentiate with 4 on both sides. Over here, 4 to the power of log base 4, those cancel. Over here, 4 to the 3rd, that's 64. Yes, the original was a log, so I should plug that back in. Log base 4 of 64 could be rewritten as log base 4 of 4 to the 3rd, because 64 is 4 times 4 times 4. And then I could use my power property to bring down that 3. And what is the log base 4 of 4? That's right, it's 1. And so I get 3 just like I was supposed to. All right? Okay, I know, these have been fairly, reasonable. What could I do here? Log of x minus 1 equals 0. What can I do here? Well, and it's interesting because I didn't have that parenthesis at first. And so some students think about this. Maybe we should look at each of these. First, let's do this one. Okay, so x is the only thing inside the log, and the minus 1 is outside. I'm going to add 1 to both sides. Log x equals 1. What gets rid of that so that I can have x by itself? 10 to the. Remember, log is log base 10. So 10 to the power of log base 10, these are inverses and are going to cancel. But if I exponentiate on one side, please remember to exponentiate on the other. So we end up with that. Okay. If I plug a 10 in here, log base 10 of 10 is like log base b of b. That's going to be 1 minus 1. Yeah, that is 0. Good. What if I had this problem, though? How does this change things? Well, now I've got that minus 1 on the inside. I have to get rid of the log before I can access that. And I'm still going to exponentiate with 10. 10 to the 0? Ooh, 10 to the 0 is 1. Plus 1, plus 1, x equals 2. If I plug a 2 in here, 2 minus 1 is 1. The log of 1 is 0. Sure it is. We've seen that on our graph. What's the ordered pair here? 1, comma, 0. So if I have the log of 1, that's what's the y value on the log graph at x equals 1. The y value on the log graph at x equals 1 is 0. So log base 10 of 1 or log of 1 is both going to be 0. All right, what's next? Well, how about this one? I really want to look at those. But first these. All right, so how about this? Log base 4 of x equals log base 4 of 8 minus x. So what are we going to do here? Yes, exponentiate. I love that idea. Some people don't. And I'll show you some of those alternate approaches in a moment. If we exponentiate with 4, these cancel, and I'm left with x equals 8 minus x. If I add x to both sides, I get 2x equals 8, or x equals 4. If I plug a 4 in here, 8 minus 4 is 4, so I'm going to have the log base 4 of 4. And over here, if I plug a 4 in there, I've got the log base 4 of 4 again. And so that means yay. I do want to check to make sure that when I plug my x value in, it doesn't put me in the position of taking the log of 0 or taking the log of a negative number. And I don't have that here, so I'm good to go. There are some other ways to deal with this problem. Some students like doing log base 4 of 8 minus x. Some like moving everything to one side because they that's just something they heard and that's what they do, even when maybe that's not really the right thing to be doing or the most efficient thing to be doing. Because now I've got these two logs joined with subtraction. So I could combine them into one log with division. Now, I'd like to get rid of this log, and that's going to require me to exponentiate both sides. These will cancel. 4 to the 0, x over 8 minus x. Oh, look, an equation with a fraction. Do you remember me saying that we need to multiply both sides by that denominator to clear out the fraction? So here I have x equals 8 minus x. And look, I'm going to add the x, have 2x equals 8, or x equals 4 again. This will work. There's nothing wrong with this. I get the right answer. It's just a little more labor intensive. And, you know, I generally find that math and I get along better when I'm not always feeling like I'm doing the problems always the long, hard way. Okay, how about this one? Log base 5 of x minus 2 equals log base 5 of 3x plus 7. Give it a try. Okay, did you exponentiate with 5? And so we have x minus 2 equals 3x plus 7. Well, if I subtract x from both sides and subtract 7 from both sides, I'm going to end up with minus 9 equals 2x, or x equals negative 9/2. Woohoo! Good? No. Because if I put negative 4.5 in here, negative 4.5 minus 2 is going to be negative 6.5. I can't take the log of a negative number. So that one doesn't work. Likewise, if I had plugged this in here, this is going to be negative 27/2 over 14/2. Well, it's going to be negative 13/2. And that's not something I can take the log of. Can't take the log of a negative. It's not that this number is negative. It's that when I plug this number back in, I'm asking log to take the log of a negative number. And that's where the problem occurs. Okay? So, no solution on that one. How about this one? Log of x squared equals log minus 3x minus 2. Give that one a try. I hope you are comfortable with that one. Hey, welcome back. Did you exponentiate with 10 on both sides? And so we get x squared equals minus 3x minus 2. In our algebra basics unit, we said if we ever see degree higher than 1, we want to move everything to one side. And then we can factor and set each factor equal to 0. So I get x equals negative 2, and I get x equals negative 1. Well, negative 2 squared is positive 4. I don't have a problem with negative 2 in here. What about over here? Negative 2 times negative 3 is positive 6. 6 minus 2 is 4. I can take the log of positive 4. That's exactly what I had over here. This answer works. Don't throw away all the x equals negative number things because you think they're not going to work. This negative did work. Okay. So what about plugging in a negative 1? Same here. Negative 1 times negative 1 is 1. I can take the log of 1. And if I have that negative 1 in here, negative 1 times negative 3 is 3. 3 minus 2 is 1. And so I get the log of 1 equals the log of 1, and this works as well. All right? Okay. We will explore more extraneous solutions tomorrow or in the next video. Let's just do a bunch of different things, and then we'll call it quits pretty shortly now. For example, log base 3 of x minus 4 equals 2. What do I do here? Well, what gets rid of a log? That's right, our new verb, exponentiate. These cancel. I have x minus 4. This isn't 3 times 2. It's 3 raised to the second power. And so I have x equals 13 as my answer. Since this is a log equation, this is must check. I plug that in. 13 minus 4 is 9. Log base 3 of 9. Well, isn't that the same as log base 3 of 3 squared? And then I use that power rule to bring down that 2. And what's log base 3 of 3? Right, it's 1. And so I get that same 2 that's over there when I plug in x equals 13. How about this one? E to the 2 ln of x equals 9. What can I do here? Yeah, there's a problem with that though. And the problem is that if I try and take the ln of both sides here, well, I guess I could, because then I would bring that down to ln of x, ln of e equals ln of 9. Ln of e is, that's right, 1. Good, I'm glad you're starting to remember that. And I need to divide both sides by 2. And now how do I get rid of this? I've got to exponentiate. And these cancel. X equals e to the ln of 9 divided by 2. And that's a little ooky. It is a little ooky. So let's take it a little further. E raised to the, instead of writing this as ln of 9, I'm going to do 3 squared over 2, because now in the here with the ln, I can bring that 2 down. I'm going to have e to the 2 ln of 3 over 2. These cancel, right? 2 on top, 2 on the bottom. Now I have e to the power of log base e. Well, they cancel. I'm left with 3. The answer to this problem is 3. And boy, it didn't look like 3 until the very end. So that's not how I would do this problem, by the way. That's how many students do this problem. When I think about this problem, I think about moving this up here. Moving this up here with the power rule. ln of x squared equals 9. And the reason is because now I see e to the power of log base e. These are inverses and cancel, and I get x squared equals 9. If I take the square root of both sides, don't forget you have that plus or minus, and the square root of 9 is 3. If I plug in a positive 3 here, sure, I get ln of 3, no problems. But if I take this negative 3 and plug it in here, then I'm trying to take the ln of negative 3, and that just doesn't work. So I only have one solution here, x equals 3. All right, well, I think that's where we're going to stop for today. I hope you have a wonderful rest of your day, and I look forward to seeing you in assignment 70, which will be, there was one more. Yeah, we'll do it in assignment 70. Have a wonderful day, everyone.